My name's Joel Titus, and my project is estimating calories burned during exercise using machine learning techniques. So a quick overview of the table of contents. We're going to go into the project introduction, the literature review, proposed framework, case study, and summary, and future studies. For weight loss patients, monitoring the number of calories burned is very important. Patients need to estimate the number of calories burned from exercise so that they can balance their net calorie intake. They do not want the calories burned and the intake to differ. To accurately predict the number of calories burned, this project will use machine learning models that will take predictors to make the estimations. So our literature review will help us understand the problem a little bit more. So the best technique to estimate the number of calories burned during exercise is to use a device called a metabolic cart. Why this method is the best is that it produces a high level of accuracy by measuring the amount of gas exchange from respiration during exercise. So as people exhale, we release carbon dioxide, and when we inhale, we take in oxygen. So this cart can measure the amount of oxygen burned. So there's a well-studied conversion rate of 3.5 milliliters of oxygen per kilogram of body weight per minute is equal to 1,000 calories per body weight per hour. This is important because we can get the number of oxygen quantity in terms of calories using this conversion. The problem with the metabolic cart is it's a piece of medical equipment, so a weight loss patient cannot use a metabolic cart to make an estimation every day. So alternatives to the metabolic cart are sensors and sensor data, wearable devices, workout machines, things that can take your heart rate, your body temperature, GPS position, and accelerometers, easily monitor the data, and then they can be programmed to estimate the number of calories burned. So modern research has explored the application of supervised machine learning modeling to estimate the number of calories burned, because algorithms can leverage those same predictors, but they can also make estimations when a linear mathematical function fails to approximate the estimation. And so those algorithms are capturing that underlying relationship between the independent and the dependent variables. In this case, the biometric data, the heart rate, the body temperature, height, weight, age are going to be the independent variables, and the dependent variable will be the number of calories burned. So researchers have concluded that XGBoost model regression is the best model for estimating the number of calories burned. Boosting models are great when a linear formula does not fully capture the relationship. But what's a fact is that the boosting models do not have a one-size-fits-all model. So the research kept saying XGBoost, but there are other models available that were not researched. So these other models, they take weak learning small trees and they make a combination of weak learners to help form a stronger one. So our motivation for this project is to make a machine learning model that can accurately predict the number of calories burned during exercise, and we want to use readily available data like your heart rate and your body temperature to make these estimations. And the researchers have claimed that XGBoost is the best model, but there are other options out there, and we would like to test them. So the purpose of this project is to develop a framework to compare how well different machine learning boosting regression models meet the calories burned estimation problem. So our framework scheme is going to employ data acquisition, where we'll take a data set from the Kaggle.com website. It's been a pretty well studied data set. And then we're going to use Python programming language with a bunch of libraries, sklearn, XGBoost, LightGBM, and we will prepare the data so that the data works in all of the different types of models that we want to test. Our model selection is going to be the XGBoost, the light gradient boosting machine, also known as LightGBM, the CatBoost, also known as categorical booster, adaptive boosting or AdaBoost, and a linear regression. Each model will be evaluated for their fitment using the mean absolute error and R2 metrics, and we're going to do a cross-validation score to assess the model generalization. So in our case study, the first step was to create all the libraries and then to make a pandas data frame. And here's a snippet of what that pandas data frame entailed with the lower and upper bounds of some of the variables. So after the data preparation and data cleaning, we went into model training and testing. And to do this, we did a cross-validation technique. Each fold was used to test the model once, and the fold was used as training data for the subsequent iterations. The mean absolute error, the coefficient of determination R2 were some of the metrics that were generated. And then we went into evaluation and validation using the metrics, where the fitment was analyzed using the mean absolute error and R2 scores, and the generalization was used the average R2 or the cross-validation score. And here we have the cross-validation scores, and it shows that the CatBoost was the highest performing. And here we have average cross-validation score histogram, and we can see that the CatBoost, light gradient boosting machine, and XGBoost were all scoring quite high. And the mean absolute error demonstrates that those same three models, XGBoost, LightGBM, and CatBoost, all had very low errors in comparison to linear regression and AdaBoost that scored high. So in conclusion, this project showed that CatBoost outperformed XGBoost in both the model fitment and the model generalization. Additionally, LightGBM also slightly exceeded the XGBoost baseline. Linear regression and AdaBoost failed to outperform the XGBoost. One important note was that CatBoost took a lot of computing power and was quite slow during the model training and the model testing. This issue might be an item for consideration in future studies because the CatBoost just takes too much computing power for practical applications. But there are LightGBM alternatives that are still doing good. We could also look into future engineering for future analysis and future improvement. And here are some of the references that I used for the project. So if you have any questions, comments, or concerns, please email me at my Louisville email account. Thank you.